Hey everyone, Mr. Sharkey back with another exciting chemistry video. Wow. Today we're going to be talking about energy bar charts, which are a nice way for us to represent energy changes during a system. So we've already talked a little bit through your readings and your notes about thermal energy, which is energy related to motion, phase energy, which is energy related to the state of matter or the arrangement of the particles, and then these energy bar charts also include something called chemical energy, which we haven't talked a lot about yet because we've mainly been focusing on physical changes rather than chemical changes. Today, we're going to walk through some examples. So this example is in your notes packet as well as your problem set. So let's go through it together in your notes packet. So if you flip open your blue notes packet, oh, there it is. It should be towards the end of the reading that you all did. It is on the back of the first page, and it is labeled for us under energy diagrams. These charts are called energy bar charts. We sometimes also call them LOL charts because they look like LOL. You know chemistry teachers, pretty funny with jokes. So in this first example that we're going to look at together, it says that a cup of hot coffee cools as it sits on the table. The first thing we want to do is determine what the system is. The system is the thing that we care about. It's the thing that we're focused on. Based on the scenario that's been given to us, we are focusing on the cup of coffee. So that system is what we're going to write into the center circle of our energy bar chart, or inside the O of our LOL. That means that everything else is the surroundings. The system is the thing that we're focused on. The surroundings are everything else. In this case, we're starting with coffee and we're ending with coffee. Our particles are not rearranging to form a new substance, so that means that we have a physical change. When we have a physical change, we can ignore the chemical energy because chemical energy is only involved during chemical reactions or chemical changes. We're going to use this chart to assign a certain number of bars to the different types of energy. So let's start off by talking about phase energy. Phase energy is due to the interactions between particles. The energy is stored in solids, liquids, or gases. Solids have the least amount of energy. Liquids are somewhere in the middle, and then gases have a whole lot more phase energy than the others. If we think about why that is, solid particles are usually closely packed together. They're vibrating around just a little bit, not moving a whole lot. Liquids have a little bit more motion. They're able to slide past each other. And finally, gases are zipping around real quick and moving with a lot of energy. So when we fill in an energy bar chart, we want to give solids 1 bar of energy, liquids will get 2 bars, and gases get 4 bars. In order to write this information down so you have it in your notes, I would encourage you to either write it somewhere in this LOL diagram in our notes packet, or you can include it on the inside cover of your notes packet. But I would pause the video here for a second and record these different values for phase energy. When we get to our energy bar chart, we can actually fill in that number of bars depending on the phase of matter that we have. So if we think about our coffee, initially our coffee is a liquid. So when we get to this EPH section of our chart, we are talking about the phase energy. And since it is a liquid, we're going to fill in 2 bars worth of energy. After our coffee has cooled down a little bit, it is still a liquid. It's not going to freeze and become a solid. So after the change, we still have 2 bars of phase energy. We've already said that we're not going to worry about chemical energy because we don't have a chemical change. So the last thing we need to look at is our thermal energy. When we're talking about thermal energy, here's our breakdown. It's this bit down here. I recommend you copy this in the same spot you put those phase bars. If we're talking about something that's hot, we're going to give it 4 bars of energy. If something is warm, we're going to give it 3 bars. If something is room temperature, we're going to give it 2. And finally, if something is cold, we're going to give it 1 bar of thermal energy. Now, these aren't necessarily hard cutoffs. These are just kind of giving us an idea of how much energy something has. If we think about it, if something is very hot, those particles are going to be moving around very quickly. There's a lot of energy inside something that is hot. Meanwhile, if something is cold, it's going to be moving a little bit slower. There's not quite as much energy involved. So that's where we get this idea: more bars for hot, fewer bars for cold. If we look at our coffee cup example, we're starting off with a hot cup of coffee, so we're going to fill in 4 bars of thermal energy. And we're letting that coffee cool in the room, so it's eventually going to get down to room temperature. So in our final box, we can show that we have 2 bars of thermal energy. So now we've kind of assigned all of the bars for our energy bar chart, but we aren't quite finished. The main focus, the idea of these charts, is to give us an idea of what the change in energy is. So the last thing we're going to do is fill in a little bit about the change of energy. If we look, we have a total of 6 bars on the left and a total of 4 bars on the right. So that means that our final situation has 2 fewer bars. That means that 2 bars must have left the system. As our coffee cup was cooling down, it was losing energy. So the last thing we want to do is we want to show that 2 bars are leaving the system. So we can draw 2 bars with an arrow pointing away. And then we can also say that there is a negative Q value. Q, in this instance, just stands for energy. So if we have a negative Q, that means we are losing energy. When something is losing energy, we call that exothermic. If something is gaining energy, we call that endothermic. So the last thing we could do is we could say that this is an exothermic exchange. We're going to look at another example here. This one is going to be looking at a phase change. So it says that a tray of ice cubes at negative 8 degrees Celsius is placed on the counter and becomes water at room temperature. Take a second, draw another LOL chart below the one in your notes, and I want you to pause the video and see if you can work through this example. To get us started, we want to think about the system, which is going to be our tray of ice cubes. The ice cubes themselves are the things that we're going to focus on. We know that the solid water turns into liquid water, so it's not an example of a chemical change. A little hint, none of the examples in this unit are going to be chemical changes. We're mainly focused on physical changes for now. If we think about the phase energy, we're going from a solid to a liquid, so our phase energy is going to increase. Also, the temperature is rising, so we're going to increase our thermal energy. So if you haven't yet, go ahead and pause and see if you can fill out what our energy bar chart would look like. Welcome back. If you followed along, your energy bar chart should look something like this. The choice in the thermal energy bars is arbitrary, but we need to be consistent. So since we're starting off cold, in this example, we can see, we can see that there's about a half of a bar of energy, just to show that this is starting off as really, really cold ice. The phase starts off as a solid, so we only have 1 bar under the initial. When we get to the final, we've heated our ice up to room temperature, so we're going to have 2 bars of energy there, and then we've become a liquid, so we have 2 bars of phase energy as well. This is your energy bar chart should look something like this. You may have chosen something slightly different for the thermal bars, but the main focus is that it should be less than the room temperature. In this instance, we actually have energies getting added to the system. So now, when we fill out our final bit about the energy transfer, we want to show that 2.5 bars, instead of leaving the system, are now entering the system. So I've drawn an arrow pointing in, And this time around, our Q is positive because our system is gaining energy. It's pulling energy in from the surroundings. So we would call this an endothermic process because heat is entering the system. Um, that is all that I have for you today, these two examples. There are some more in your problem set, so go ahead and take some time to work through those. And if you have questions, reach out to your chemistry teacher, and I'm sure that they would love to help you. Thanks so much for watching this video. Be sure to smash the like button and subscribe and hit the bell to get notifications about future uploads. And finally, check out the Patreon in the description. You can get some awesome Mr. Sharkey, Mrs. Cat, Mr. Horner, Miss Bellotti, Mrs. Drudge, and Mr. Hambley merch. It's going to be a really cool place to check. Just kidding. There's not a Patreon. But I hope you're having a good day. Bye.